Hello. Welcome to everyone joining us from around the world today. I'm Katie Fehrenbacher, and I'm a journalist covering climate tech and clean mobility. I'm excited to welcome you all to another installment in the QuantumScape webinar series, and I'm tuning in from my home office in sunny San Francisco. Today, we're going to be digging into 4C, ultra-fast charging for electric vehicles. We'll discuss how this works, what are the barriers with current charging technology, and how this level of fast charging could help bring EVs into the mainstream. First, we'll listen to a presentation including new charging data from QuantumScape, and then we'll discuss fast charging technology and the market landscape with our great battery experts. But before we begin, I just want to do a little bit of housekeeping. This webinar is being recorded, and it'll be posted on quantumscape.com as well as QuantumScape's YouTube channel after the event concludes. Throughout the presentation, please feel free to submit questions by using the Ask Question box on your console. You can see it right there. We'll be fielding those questions and we'll select as many as we have time for. You can also adjust any of the screens that you see right in front of you in the console to fit your viewing preferences. You can move the slides, make them bigger. You can make the video chat bigger. You can make the Q&A bigger. And so now I'd like to kick it off and introduce our panelists. First, we have Will Hudson. He's the Vice President of Product for QuantumScape, and he'll take us through the charging data. We've got Paul Albertus, who is Associate Director of Chemical and Biomolecular Engineering for the Maryland Energy Innovation Institute. He's also the former Program Director for RWE. And finally, Otmar Biche. He's the Head of E-Mobility for Porsche. And we're very grateful to have all our speakers with us today. And we're very grateful that all of you have tuned in as our audience members. Thank you so much. All right, now I'm going to kick it over to Will to take us through the charging data results from QuantumScape. Will, over to you.
Okay, yeah, thank you, Katie. Thanks for the kind introduction, and thank you to our audience members for your attendance. Again, I'm Will Hudson. I'm the VP of Product at QuantumScape. And I'm very excited to be discussing fast charge results today. So let's get started. First, I've been asked to read a disclosure by our legal team, so I'll get that out of the way. My presentation contains forward-looking statements within the meaning of U.S. securities laws, including data analysis and models based on management's current expectations, and involve significant risks and uncertainties that could cause the actual results to differ materially from the expected results. Further information about risk factors that could materially affect QuantumScape and its technology can be found in our filings available on sec.gov. Okay, so let's jump in. I'll start with an agenda. I want to begin by answering the question, why 15-minute fast charge? We'll look at the existing landscape of EVs with lithium-ion cells and what some of the challenges are that keep these vehicles from charging faster. Then we'll look at QuantumScape's approach, so our unique lithium metal solid state architecture, how that helps to address some of those fast charging challenges. And we'll end with the data before our panel discussion and Q&A. So what is the market requirement in terms of range and charge time for EVs? Well, in our view at QuantumScape, the requirement is set by the existing technology. So the incumbent internal combustion engine vehicle. It's so convenient, in fact, that we don't even think about it. So it's almost trivial to buy a car that can drive 400 to 600 miles on a tank of gas. And when we do fill it up, it won't take longer than 5 to 10 minutes. So it's our thinking at QuantumScape that the consumer, the customer, is unlikely to be willing to accept something significantly less than that. So we believe the EV requirement will be in the same range, something like 400 or more miles of range with a charge time between 10 and 80% of 15 minutes or less. And then importantly, the ability to repeat this fast charge, right? To not have to worry about, will I be damaging the battery system by going to the fast charger? And so we think something like 400 cycles will be enough. If you think about a 400-mile range with 400 cycles, that's more than 150,000 miles of accumulated charge. So what is the landscape today? I have two examples here. I've kind of categorized available lithium-ion cells into either the power cell category or the energy cell category. We'll talk about this as we go. In reality, it's not just two buckets. There's really sort of a continuum between power and energy, but I think it's helpful to look at it this way. So a good example in the power cell case would be the Porsche Taycan. And for full disclosure here, Porsche is a member of the VW Group, and they are an investor in QuantumScape. But I stand by the statement. I think that this is a best-in-class, exemplary vehicle. And what they've been able to do is get the charge time down into the 20-minute range for 10 to 80%. So that's pretty compelling. But it doesn't have class-leading range. So maybe it's in the mid to low 200-mile range. On the other end of the spectrum, another interesting vehicle would be the Tesla Model S. So in this case, the range is higher, maybe as high as 400 miles, but the charge time is slower. So the numbers that I've seen are more like 35 minutes from 10 to 80%. And so you can already see the compromise that the consumer is making. And what QuantumScape is trying to do is reduce or eliminate that compromise. So another way to look at these lithium-ion cells and sort of how they compare to one another is with a chart like this. This is a Ragone chart. And it shows the cell level energy density in watt-hours per liter versus the cell level power density in watts per liter. And I've placed the cells that go into these two example vehicles onto the chart. And what you see is that they both fall essentially on a frontier. Because they are based on the same underlying architecture and the same basic materials, they can sort of shift in either direction on the chart towards higher energy or towards higher power, but not just anywhere. Where we'd like to be, of course, is higher, which means more energy density or more range, and further to the right, which means more power or faster charge times. So if you look at these dashed gray lines, these represent constant ratios between the energy and the power. So anywhere on this first line, which says 1 hour charge, means that we can deliver that energy in 1 hour's time, but not faster. If we work our way to the other lines, we go to a 30-minute rate or even a 4C 15-minute rate. And so you can see that we'd like to be sort of over here and to the right. And one last point on this chart before I move on is that there is a difference between charge power and discharge power. So discharge power would be like the acceleration of the vehicle. And you may be thinking, well, the Tesla Model S goes 0 to 60 in 2 or 3 seconds. It does have a lot of power, but it's still limited in its charge rate. And we'll talk about why that is. So here is some actual fast charging data. This chart on the left shows the charge power in kilowatts versus state of charge for a range of different vehicles on the road today. The Porsche Taycan is the one in yellow here. And I think Otmar has told me that they already have improved upon this rate. What I want to point out here, though, is that there are some differences in the charge acceptance of the different vehicles. But in all cases, there is a tendency or a trend towards lower charge rate with state of charge. So what that means is that if you were to show up at the supercharger with your pack nearly fully depleted, let's say 10%, you could expect a faster charge rate. But if for whatever reason that wasn't possible and you pulled into the charger at more like 50% state of charge, you're going to have to go slower to add the same amount of range. And that's another issue, another challenge with existing technologies. Another way to look at that is on the right. So this chart is the state of charge versus time for just one vehicle example, but it makes the same point. So initially the slope here is higher, which means the rate of increase in charge is faster, but over time that rate decreases and we have this plateau behavior. So now I want to talk a little bit about where those limitations come from. And there's really two reasons. And in order to understand this, it's helpful to look at the structure of a lithium-ion battery. So I have a schematic here, fairly simple. This is a sort of a cartoon of a unit cell, the lithium-ion cell. And you can see a couple different components. So we have a porous cathode composed of active material particles on the bottom. We have a porous anode, typically composed of graphite particles on the top. and then these are separated by an insulating plastic layer that we call the separator. This is a porous structure, and the whole system is flooded with a liquid electrolyte. And that's important because that's the medium that in which the lithium ions are transferred. And so the way the system works is it's kind of like rolling a ball uphill and then letting it flow back down. The lithium ions start in the discharge state within the cathode, and when we charge it up, we move them through that liquid, through the separator, up to the anode. When we use the battery, they will flow back downhill, along their potential gradient back to the cathode. And what dictates the rate that this can be done is basically how fast or how easily those lithium ions can move. And so there's two length scales that we care about. The first is a short range diffusion. So as we charge the cell, the lithium ions move up to these graphite particles, and then they have to basically move into the lattice of the graphite structure. And that can only happen at a certain rate. That's basically dictated by the fundamental material properties. So what is the length scale of the lattice? How big is the lithium ion? And so on and so forth. There's some things we can do, like change particle sizes, but only so much. So that's basically fundamental. The other length scale that we care about is the long-range diffusion. So again, when we charge, we're moving lithium ions from the bottom to the top. And the thicker we make that cell, or the longer that path length, the slower it's going to be. And this we can refer back to the energy power trade-off that we already talked about. In order to get more energy into a cell, we'd like it to be thicker, but that will come at the expense of charge rate. So the other thing I want to look at, another limitation, is what happens if we charge too fast. So on this slide, I have a chart on the left that shows the graphite lithiation potential as a function of how much lithium is in the graphite structure. That's basically the state of charge. And what you're looking at is a potential on the y-axis that's relative to the lithium plating potential. So that would be at 0. And what you see is this downward trend of that potential as a function of how much lithium is in the graphite structure. And what happens when we're charging is that there's a resistance to this lithiation process. That's, again, a fundamental property. And the faster we go, if you think back to sort of high school physics, you have V equals IR. So the faster we go, the higher the current, or I, is, the larger the V voltage or overpotential becomes. And when we plot that overpotential on this graph, it actually goes in the downward direction. So if we charge too fast, we can drive the voltage down, and at some point we will cross a threshold. And that's important because when we go below 0, it becomes favorable to actually plate metallic lithium instead of insert lithium into the graphite structure. So another way to look at that is over on the right. We have our battery structure, and I've just zoomed in on a particular particle. And the intended operation for this type of cell is that these green lithium ions go into the lattice and meet up with an electron. But again, if we're piling up lithium at the surface and the lithium can't get in fast enough, the potential drops, we can actually plate a lithium deposit on the surface. And if that happens, that can cause problems. So lithium is going to react with the liquid electrolyte. That can cause resistance growth. It can cause capacity fade or decrease in range for the vehicle. And in the worst case, it can form a dendrite, which could short the cell and cause failure. So now I want to look at a little bit of real-world data. This is publicly available data. The authors here surveyed several thousand vehicles, EVs, actually driving around on the road. And what they did is just group the data into 3 different categories. So we have vehicles that were never fast charged, so never DC fast charged in blue. We have another group that were fast charged between 0 and 3 times per month. And then this last group that was fast charged more than 3 times per month. Okay? And what you can start to see is a separation between the groups. So this does not necessarily mean that if you fast charge today's vehicle, you will cause damage. It just shows that that's possible. And the system designer has to be really careful to manage how this is done. So now let's switch gears a little bit and talk about what QuantumScape is doing. I refer you back to the conventional lithium-ion cell structure on the left, and what QuantumScape's architecture looks like is over on the right. And so you'll see a couple of differences. So first, the cathode is fairly similar. It's a high energy cathode, but what's missing is this whole anode, this whole host anode structure. Okay, so as a result of that, we have significantly more compact and simpler cell. The second thing that we did was remove this plastic separator and replace it with a dense, solid ceramic. That's really important. We'll talk about that more. This material needs to be resistant to dendrites, because what we're going to do is when we charge the cell, instead of move the lithium ions up into a host anode structure like the graphite, we will plate it as metallic lithium, and that is depicted by this green layer here. So you can see visually where the energy density advantage comes from. We have just as much energy in this structure here that takes up a lot less space than the conventional cell. But how and why does it address the fast charge challenge? So that's the next question. Well, if you remember back to our diffusion limitations from the conventional system, we've basically addressed both of them. So firstly, the short range diffusion, the rate at which lithium could enter those host particles. We don't have a host material here, so that's no longer a problem. Instead, what we have is a single planar interface between the separator and the lithium metal, and that's a very fast interface. And this is a key point because not all solid-state separators have such a fast interface. Many of them are actually high resistance, and that will limit the current density. But the material that we've used and put into our cells is very, very fast, and so we'll show you that in the data coming up. The second thing, which I already mentioned, is that we have a material that is resistant to dendrites. This is important because especially when we're trying to charge quickly with high current density, if the material is not dendrite resistant, you can quickly form dendritic shorts, which can cause failure. And then the third thing is the path length, the longer range diffusion. I'll just quickly go back. The conventional cell has a much longer path that lithium has to travel. And in QuantumScape's system, we've removed that anode so the path length is shorter. And so these combined advantages allow us to charge more quickly. These are the materials that we make. So on the left is a picture of the actual ceramic separator. This is the material that goes into the devices themselves. In the middle is a picture of our single layer pouch cell. This is our commercial area format and a really important platform for us. So the data that I'll be showing today is from this single layer device. And we use this frequently to introduce improvements to our cell, introduce new technologies. And as we do that development, we will transfer those improvements to the manufacturing group, which builds them into multi-layer cells and ultimately the commercial device. So now let's look at some data. So I refer you back to this chart. We have state of charge on the y-axis and time on the x-axis. For reference, I have a conventional fast charging curve. It shows the state of charge going from 10 to 80% in about 35 minutes. And to remind you, we think the target is more like 15 minutes here. So anything in the green box should be, or green triangle should be considered good. This would be on pace for that target or faster. And so this is data that we've collected from our single layer cells. This is 25 degrees C fast charging data. And what you can see is that we reached the 80% threshold in less than 15 minutes. In fact, more like 12 minutes in this case. So we think, I want to highlight that this is 25 degrees C data. There are other solid state systems that are not capable of charging quickly at relatively low temperatures. And so we're obviously excited about this result. I also want to go through the parameter table here to be clear about what we're testing. This is a 4C continuous rate. But the way we run this test is that we bring the cell from 0 to 10% at a C/3 rate. And then sort of as if we're assuming the customer pulls into the fast charger at 10%, we go straight to 4C. And that 4C rate for this cell is 13.3 milliamps per centimeter squared. That's based on a relatively thick high loading cathode of over 3 milliamp hours per centimeter squared. So as I mentioned, it's 25 degrees. This is the same anode-free lithium metal system that I showed in the previous diagram. We are running 100% depth of discharge or state of charge. So we start at the bottom and we go all the way to 100 in our commercial area with modest pressure again and a single layer. Let's add to that. This is another data set now running at 45 degrees. And in some ways, this is actually more interesting data. We think that in a real world situation inside a vehicle, the cell temperature is likely to be somewhat hotter. That's because at these high rates with the resistance within the cell, we will generate some heat. So 45 C is actually a really good approximation of a typical fast charging temperature. And so we wanted to test that case. And what you see, unsurprisingly, is that because the resistance is a little bit lower, we can actually charge from 10 to 80% in less time, more like 10 minutes here. The other conditions in this case are the same. One other thing to look at with this raw data, these are the same two cells, but I'm just focusing in now on the C rate. So equivalent to the current density for these charging cases. And what I want to highlight here is that in particular at that 45 degrees C temperature, we're able to maintain a constant high rate almost all the way to 80% state of charge. So that's important. If you think back to the supercharger or fast charging curves that we looked at earlier on, you remember that they tended to taper as you go. And so what we're able to do here is, again, sustain that rate most of the way. And that means no matter what state of charge that you show up to the fast charger, you're going to be able to get a really fast charging rate. And again, we talked about the conditions. So those are the same here. We go C/3 from 0 to 10%, then into our 4C fast charge until the upper cutoff voltage is reached. For these cells, that's 4.2 volts. And then we do a constant voltage taper to the C/20 cut current. All right, so now this is, I think, the punchline, the most exciting result. What we did next was to repeat these fast charge protocols over and over, right, to understand the cycle life that we could get in the fast charge condition. So I have a group of cells in this case. There are two different temperatures represented, both 25 and 45 degrees C. The 45 group is quite tight, so you don't see the separation there, but there are a number of cells in both cases. And, you know, I think as is apparent from the data, we are exceeding this commercial target by quite a bit. So I think all the cells are above 90% remaining energy at that commercial target of 400 cycles. So we're really excited about this. The charging parameters are the same as what I had just discussed. And the only thing that's new here is that we do a continuous 1C discharge, which is 3.3 milliamps per centimeter squared for the full depth of discharge every cycle. Just for comparison, we did run a conventional lithium-ion EV-type energy cell, a 2170, on the same protocol. And to be clear, we do not necessarily feel that this data is representative of what you'd expect from all 2170s or all lithium-ion batteries, but it's still an interesting comparison point. Testing existing energy cells on a fast charge protocol like this is likely to damage them. So we wanted just to be able to show that, that difference. And so that's the cell level data that we want to look at. I want to spend a couple minutes now talking about the implications at the system level. So this chart on the left shows the system parameters for a top-selling EV on the market today. Think about 80 kilowatt hours in a pack volume of about 335 liters, and you might be able to drive, you know, in this case, something like 350 miles. And so now if you assume a lithium metal solid state architecture with much higher energy density, what you can expect is to increase the energy that can be stored within the volume, the same volume, and therefore increase the range. And so that's potentially compelling. But what would be more compelling is if you can get that range advantage with the 15-minute fast charge. So let's look at what that might look like. So what I did here was plot a fast charge road trip. I just mapped out a route from Palo Alto to Eugene. For you college sports fans, this is a 560-mile trip, and we looked at 3 different scenarios. So on the left, we took some round numbers of 500-mile range with 15-minute charge from 10 to 80%, and I compared that to a power example and an energy example from conventional technologies. So let's assume 225-mile range with a 20-minute charge, or 350-mile range, but with a 40-minute charge. And what you see is, first of all, the QS approach can get you there with a single stop, of course, a 15-minute stop, and these other 2 approaches require either 2 or 3 stops. And because the stop is longer, you're going to spend, obviously, more time. You end up saving between 45 and 65 minutes on a route like this, which we think is obviously compelling. So finally, here on this slide, another interesting way to look at the combined advantage of increased range with faster charge times is to calculate the average number of miles that you can add at a charger every minute. So the way to make this number faster is to both increase the range and increase the charge rate. And so if you just do the calculation based on the numbers that I show here, you can find that for every minute you would spend at a charger, in this left case, you would add 23 miles to your range. And that's compared to only 8 or 7 for the other 2 examples, so a multi-factor improvement. And so just to conclude, I bring you back to this Ragone chart and remind you where the existing frontier is. And if we add to the chart QuantumScape's commercial target, this is what it looks like. So we are trying to build a cell with around 1,000 watt-hours per liter with a 15-minute fast charge, which gives a step change on this energy versus power chart. And so that concludes my portion of the talk, and I'll just leave it here on this slide and remind you our view of the commercial requirements and what QuantumScape is trying to build.
Great. Thank you so much, Will. Interesting data. A lot of comments and questions coming in. I'd like to turn it over to our panelists now to get their take on some of this information. Otmar, let's start with you. Why do you think, why is fast charging important for electric vehicles in general? And would love to hear your kind of thoughts on some of this QuantumScape data that Will just presented on.
Yeah, thank you, Katie. For Porsche, it's really important, and as you have seen with the Taycan, we brought the first vehicle on the market with an 800-volt system dedicated from the beginning for high power and also very fast charging. And this is also the way we want to continue. And so that's why our clear target is to get down to about 15 minutes and maybe even below that, but 15 minutes would be fine on a vehicle level. And sure, we want to increase the range, but not significantly, because we think for typical driving, everyday driving, 300 miles, maybe 400 miles are fine of customer range. And what we benefit in the future in terms of energy density, we want to reduce the pack size and the weight of the battery pack. And this gives another advantage in terms of cost, but also energy efficiency on vehicle level and vehicle dynamics. And so, and if customers are really going on a long-range trip, fast charging gives them the comfort they are used to have today from combustion engine type cars. And so, and even if you look on the mass market, going normal sedans, and it's fast charging also could be of interest for people and customers who have no possibility to charge either at home or at their workplace. And if fast charging comes into the range, which was demonstrated right now, you can recharge your EV like a combustion engine type car today. And I think if you really look on big market acceptance for EVs, that's a key feature. And so that's why from the car makers, we think fast charging is really necessary for the success of the EVs on the long run.
Great. Thanks, Otmar. Paul, from your perspective, what are some of the barriers for fast charging and specifically fast charging with lithium-ion batteries, the standard out there today? Would love to hear from you.
Sure. Thanks for the question, and glad to be here to discuss this topic. In terms of the limits for fast charge for current lithium-ion technology, I think I largely concur with what Will said in terms of really the need to limit the charging rate for a very large fraction of the SOC window. That's really a big issue. And as Will pointed out, that's at least in part related to the issue of lithium plating at graphite, at the graphite anode. And of course, while you can design lithium-ion cells for faster charge, I think I saw a few questions coming through about claims made with very high charge rate lithium-ion cells. There's typically trade-offs, and really kind of trade-offs that can't really be overcome in terms of electrode thickness or the properties of graphite particles, things like that. And so this kind of power energy issue is always present for lithium-ion cells. In terms of looking beyond lithium-ion, I think that probably the biggest opportunity is to improve on current lithium-ion cells is to increase the energy stored per mass and volume. And there's a few ways to do that. Obviously, you can shift to a lithium metal anode, which is what QuantumScape is presented on here today. There's a few other approaches as well. Obviously, silicon anodes is one, not the same theoretical promise as lithium, but would offer an increase over graphite. But in terms of what I've seen so far out there, there's very limited fast charge data shown for some other solid state approaches out there that have active materials and cell designs that could really significantly surpass the energy content of lithium-ion cells. And that also include all the details you need to really look at, test conditions, cell designs, to really assess the significance of the work. Gotcha.
All right, Will, I've got a question for you about the charging data. So, you've clearly shown that QuantumScape is demonstrating this 15-minute or less fast charging with individual battery cells. So, how does the company get to, manufacturing an actual battery pack and getting that into an EV?
Yeah, that's a fantastic question. And so I think to answer it, it helps to just discuss a little bit about our development methodology. So what we've had a lot of success with in the past and continue to use is this approach of first testing and iterating and learning about improvements to the system and introducing kind of this new functionality in the single layer cell. It's a sort of low cost, like fast to learn platform. And so we do that here and we get comfortable. We build up enough data that we understand how the system works. And then what we do is we move it forward. We mature it into the multi-layer platform. And so you should fully expect that that's what we intend to do here. We'll be building multi-layer cells. Our manufacturing team, in fact, will be building multi-layer cells targeting these same rates of charge. And then ultimately that would go into our commercial product.
Gotcha. And then similar question from an audience, which you can probably expand on, but can you explain why the results aren't presented for your more recent 10-layer cells rather than your more than year-old single layer versions?
Yeah, so it's a really similar question, and it's a good question. And the answer is the same. So basically, we start with the single layer results. We've been able to show already that what we can do in single layer is transferable to the multi-layer. So we've released C/3 and 1C, in fact, cycle life data that shows the same trend of behavior. So we know that we can make this transfer, but we're releasing sort of these new results that we're excited about in the single layer platform, and we'll look to move that into the multi-layer next.
Thanks, Will. All right, Paul, I wanted to come back to you. For an audience question, they say, it seems like there's a wealth of papers on battery science breakthroughs based on different materials and innovations, yet these don't seem to come to the market very often. Why is the innovation cycle not more rapid in terms of actual market availability? And do you see that changing?
Yeah, great question. Obviously, sometimes it seems like there's a battery breakthrough every day, right? And keeping track of them can be hard. I think a little bit of historical perspective there can be helpful. And so if you look at just the timeline of how long it took lithium-ion to go from early stage type research into commercial products, and that was probably over 10 years. And obviously, there's been a huge pipeline of innovations introduced into lithium ions. So compared to the first introduced lithium-ion cell, the cells today are at least 10 times cheaper and have probably 2.5 or even 3 times the energy content per mass or volume. So that pipeline has been very strong. I'd say that the kind of innovations that QuantumScape is attempting here or working on here, introducing lithium metal, that's really a fundamentally different kind of cell and requires a very different approach. It's not an incremental advance to lithium ion. And so that's a hard problem. And I think QuantumScape has been clear. It's been 10 years and hundreds of millions of dollars. That's kind of the scale of the problem, at least potentially, to address some of these very deep technical challenges. The one thing that's changed a bit, I'd say, is that there's a huge market now. So historically, high energy density batteries provided mostly for portable electronics, which is a big market and it's growing, but automotive is at least a factor of 10 higher in terms of market volumes. And so the level of interest, the level of investment, the ability to address some of these technical challenges and then translate them into commercial production on kind of a faster timeline, that's a good reason why this might happen a little bit faster than what we might have expected historically.
So do you see the automotive industry condensing that innovation pipeline from kind of R&D to mass manufacturing to go along with the boom in EVs?
Well, if we look at what the OEMs are doing, they certainly are interacting with early stage companies. And that shows the level of interest and how deep they're interested in going into early stage companies and keeping track of what they're doing, becoming investors, cultivating them, et cetera. I guess the countervailing point of that, of course, is that automotive is also a really tough market in terms of requirements. A small phone battery or a small watch battery is just a very different type of product than what you need for a field deployed vehicle type application. And so it's maybe the two sides of that question. Even as there's more investment and attention, it's a tough market to actually become a supplier for.
All right, Otmar, I want to go back to you. How does Porsche consider fast charging requirements? Is the focus on low charge to full charge, or are there use cases around a battery pack at 50% going to a high state of charge? What would that customer experience look like if so?
So on the long run, we really would be interested to widen the window where we can apply the full charging power. So today, we can apply the full charging power up to about 50% state of charge, and then we have to decrease the charging power. So we really would be happy for our customers and for our vehicle performance if we can exceed this window up to about 80%. So because then even if you arrive at a charging station with 40% state of charge, you can go up to 80% again. So I think that would really be a good feature for our customers.
Interesting. And Otmar, I'm going to follow up with you again. Porsche must evaluate a lot of emerging battery technologies. Have you seen any emerging technologies with higher power and higher density than lithium ion?
No. So today we use lithium ion with a small amount of silicon in in the anode. So we think in short term, we can, by increasing the silicon amount in the anode, we are able to increase energy density and fast charging performance. But on the long run, we need technologies like shown by QuantumScape to really have full fast charging capability and without compromising the range and the weight of the car.
Yeah, and I'm sure you've seen a lot coming through. All these battery makers, new battery makers, bringing samples over to Porsche. Is there things that are particularly exciting to you that have been coming through different types of batteries?
We see really good performance with silicon anodes, so that looks pretty good. So there is also good competition on solid state, but there, frankly speaking, I haven't seen anything on the solid state side with similar temperature performance and fast charging performance today.
Understood.
But I think
question.
the biggest competition is from the silicon anode side.
Okay. All right, there's a technical question for Will. QuantumScape has stated previously that 800 charge-discharge cycles should be the target before getting below 80% capacity. So why is the standard now changed to 400 cycles?
Yeah, that's another good question. And we stand by our previous statement that 800 cycles is the requirement for standard use. And I think the way to think about this is it's unlikely for a customer to fast charge every single cycle that full depth of discharge. And so we think 800 cycles with, say, a 400-mile range pack is certainly sufficient. That's going to be at or above the typical lifetime of the vehicle, like mechanical system itself. And so for this routine full depth of discharge fast charging, we think not that many cycles will be required.
Okay. And a follow-up question for you.
I would confirm this sorry for interrupting, but I would confirm this from a vehicle standpoint. So I think 400 cycles, full charging cycles are fine, because if it's 800 is nice, but it's not in real vehicle life. You never will achieve that, because you typically don't do full charging, full depletion on every driving cycle.
All right, Will, I'm going to follow up with you. QuantumScape's batteries are still a few years from production. All comparison metrics relate to current battery technology. How does QuantumScape anticipate holding a competitive advantage with battery technologies set to improve before QuantumScape goes into production?
Yeah, sure. So obviously we don't know what will happen in the next, 3, 4, 5, 10 years with existing technologies. The reality is, though, that we like to remain paranoid. We're constantly looking at what can be done. I think there's a couple things to say here. There is some fundamental limitations for existing lithium-ion batteries. So we know that they will reach a limit of performance. That being said, I think there is a little more juice that can be squeezed out of the lemon. And so we're going to see some faster charge times, and Otmar talked about that already. We're going to see some improvements in energy density. And so our thinking is we need to stay, a step ahead. So we're looking for step changes wherever possible and not incremental gains. So that's our approach, and, we just have to stay at it.
All right, an interesting question from the audience for all the panelists about safety. How do we think about safety in terms of when we're implementing these higher ultra-fast charging capacity?
So I think from our standpoint, we expect a huge step in safety, because we have no liquid flammable electrolyte in this type of cells. but we have to prove if we have other issues. But this is our actual expectation, that it should be a huge step in terms of thermal propagation issues.
What do you think, Paul?
Yeah, to build on that, I do actually, in my research group, I actually research the topic a little bit, so I shouldn't get started. It's an interesting and kind of multifaceted issue. And you can look at it from the materials chemistry level as well as obviously cell design and things like this. There's no question that basically the oxygen released from the cathode when it heats will not have any or as much liquid electrolyte around, and that's a fundamental important safety advantage. There's other interesting things also, like what's the onset temperature of self-heating. So one issue with lithium-ion cells is that even at like 80 or 90 Celsius, 100 Celsius, you get some reactions taking place, which in turn lead to additional heat generation. And so even if there could still be thermal release from a lithium metal solid-state cell, if that doesn't start until a much higher temperature, 200 C or some other higher level, 250 C, that's also an interesting kind of factor. So there's actually, it's a very interesting topic, and there's a variety of ways to look at it, and I think it's an area that requires additional analysis and careful consideration. Yeah.
Well, from QuantumScape's perspective, how do you think about safety? Are there safety concerns as the charging levels go up, as the speed capacity goes up?
Yeah, it's obviously a very important topic, and maybe the most important of all, frankly, that the batteries that go into these vehicles stay safe. And I would echo what Paul said. Frankly, I think there's two main advantages to our approach. So we've removed most of the fuel, that can react in these sort of extreme situations when something goes wrong. And we've put a very temperature and very chemically stable material between the two high energy electrodes. And so we fully do expect that the system overall will be safer, but that will have to be fully vetted, obviously, and we work closely with our partners to make sure that it really was safe enough.
And just kind of following up on safety, in terms of the just kind of standard lithium-ion batteries, is there increased safety concerns through fast charging and enhancing fast charging through the current traditional lithium-ion batteries?
I think the answer is potentially yes. As Will pointed out, the faster you charge, you have fundamental electrochemical forces that will tend to cause problems in the cell, increased degradation rates, and that needs to be very carefully controlled. And so the BMS system, battery management system, has to be monitoring carefully the cell in order to ensure that it doesn't go outside of the specified operating rate. And it's temperature, voltage, current, cell-to-cell variability. There's a whole variety of factors that need to be carefully controlled for. Yeah, the faster you charge, that's an additional stressor and needs to be taken into careful account.
Understood. Okay. And I think a final question from our audience for all the panelists: can this fast charging ecosystem be achieved with present charging infrastructure, or do we need some kind of new infrastructure rollout?
So with maybe I can answer that. So today, in the US, we have Electrify America, which is providing at least 350 kW chargers at 800 volt systems. So this should be improved to about 400 to 500 kW to get down to about 15 minutes. For a 100 kilo. So it's a little bit dependent on the pack size, but if you assume about a 100 kilowatt hour pack, you would have, you need about 400 to 500 kilowatts charging power to achieve that charging rate.
Yeah, so if I can just jump in, sorry, Katie, I completely agree with that, by the way. But just to use, I think a good example of a vehicle already on the market, if you looked at a Tesla Model 3 pack around 80 kilowatt hours and applied a 4C rate, you'd be kind of right up against the limit with existing technology. So if we want both that longer range and the faster charge time, I think there's could be a little bit of a gap there.
Yeah. But I think the infrastructure, so the charging infrastructure industry is well prepared for that. So that's why we introduced from Porsche side the 800 volt systems. So these are capable of achieving this range of required power. So if you the current CCS plug, which is used also in the US, is capable of doing 500 amps. And if you then go up to 800 to 900 volts, you can achieve more than 400 kilowatts. So that's no problem. And the systems
So you're
are
saying that... Go ahead.
I was going to say that we're usually not going to do a full charge, right? So 10 to 80 means it's only 70%. Right? So if you have a 100 kilowatt hour pack, you want to charge it at 4C, but only do 70% of it. It's the 350 kilowatt chargers are pretty close. They're pretty close.
Yeah, it's pretty close, but 400 would be fine.
Gotcha. So Porsche doesn't have to reinstall or deploy new infrastructure for this kind of coming step change. It's baked in. Okay. Will, any thoughts on the charging infrastructure question?
No, I completely agree with what's been said there. I think we'll be able to do it without, major reinvestment.
Yeah.
Okay. And I wanted to give the panelists, each of you, just a few moments before we wrap up on some kind of thoughts on overall what QuantumScape the data has presented, and in terms of 4C ultra fast charging in general, and how this will affect the EV market. What about you, Paul? Do you have some key takeaways that you wanted to get in before we close?
Yeah, I've been following this lithium metal story very carefully for quite a few years, and it's one I've followed very carefully on the research front and try to read and keep track of it. And I'd say that the data today is quite exciting to me in the sense that there's many different things that are achieved simultaneously. So high current density, the cell loading is near the commercial target, the temperature is 25C is important. As Will mentioned, hundreds of fast charge cycles for a lithium metal solid state interface with all these other conditions is something that hasn't been shown before. And so to me, that's a very significant accomplishment. And I think, scientifically and in terms of the potential for lithium metal to work, I think that's really an important step forward. So I think that from my point of view is exciting development.
Yeah. I just want to follow up with you. What are some of the physics and material challenge involved in this type of anode-free design that can fast charge at room temperature?
Yeah, so, and I didn't really get into, we haven't talked much about anode-free. So when you build it with a cell, there's already lithium in the cathode. So the cathode comes with the lithium in it. And so in principle, if you're able to make a very good cell, you don't actually need to introduce any lithium metal or foil on your anode side. And from a cost point of view, from a manufacturing point of view, that's a very big deal. And so in particular, what you have to make sure is all the lithium in the cathode goes to the anode, doesn't get sidetracked into other products that cannot result in cycling. And so in order to make this thing work anode-free, you have to have a very efficient system. The lithium in the cathode has to end up in the anode. I assume that they're not actually fast charging from the very beginning, but during the formation process and manufacturing, that process can be done. And then I think that's also an important part of this from a cost or manufacturing point of view as well.
Okay. Otmar, do you have any thoughts overall about ultra-fast charging or the QuantumScape data?
Yeah, so I'm following now for many years the developments at QuantumScape, and so I think it was a very hard time they had in the beginning, but I'm really excited also, as Paul said, from the results we see today, and I'm really looking forward to have this in a multi-layer cell, and that also the industrialization works. So I think that's now the next big step for QuantumScape to demonstrate that they can produce this on a larger scale, so that I can get cells to build it into my cars.
Yep, we'd love to see that. All right, Will, I'm going to hand it over to you to kind of give any kind of wrap up on your data.
Yeah, well, thank you very much. And first, maybe I'll take this second to thank the panelists, Otmar and Paul. We really appreciate you guys joining us. You have really insightful comments. And Katie, you too, for moderating. We really appreciate it. I guess what I would say is we're obviously really excited about these results. That's why we bring them to the audience here today. We're not aware of any other solid state systems that are capable of this level of fast charging with a energy dense cell design. That being said, there's a lot left to do, and we know that, and so our heads are down, focused on kind of finishing the task at hand. So at this point, we're really excited about what comes next and about sharing upcoming performance and manufacturing results over the coming year.
All right, thank you, Will. All right, I'd like to thank you all so much for this rich discussion today. Thanks, Will, Otmar, Paul. We love to hear all your thoughts. And I want to note to the audience, QuantumScape has added a technical white paper and a blog on this specific topic on their website. So be sure to check that out on quantumscape.com. I'd also like to give a little personal plug. If you're interested in tracking the latest climate tech startups like the future QuantumScapes that will be coming out, you can sign up for my upcoming newsletter at energize.co. And I want to thank many thanks to everyone for sharing your insights today and all the excellent audience questions. There were tons of questions coming in. We're sorry we couldn't get to all of them, but we really appreciate your attention. And thank you all the audience for joining us. We hope you've all found it interesting, and we hope you'll all join us again soon and for the next one. Thanks, guys.
Thank you.